Oh, hey, welcome back to A View from Earth, the official podcast of Fisk Planetarium at CU Boulder. We hope you're all doing well and staying safe. My name is Colin Sinclair. I am a CU undergrad studying astronomy, and when the buildings open, I give presentations at Fisk. But for now, and hopefully beyond, I also co-host this podcast. And I'm joined by my friend Tara here. Hey, Tara.
Hello. I'm Tara. I'm a planetary scientist and a CU alum, also a presenter at the planetarium when I'm lucky enough to do that. I coordinate the outreach program, some other fun stuff too. And of course, co-hosting this podcast with Colin.
So you may or may not know that we love to talk to scientists in the Boulder area about their work. And so today we're going to be talking about we're going to be talking to Dr. James Mason about CubeSats. And I actually wonder, Tara, if we should answer the question of what CubeSats are or let James do that, because we asked him that in the interview. Should we?
It is the first question that we ask him, but if anybody wants like a spoiler, CubeSats are basically just very small satellites.
There you go.
The end.
We never talked about this. The word cube, how does that fit in? Are they all cubes, like, specifically, or did they start that way? Do you know?
I think the original definition of a CubeSat is 10 by 10 by 10 centimeters.
Okay.
Like that was a CubeSat.
Right.
And so now they do other combinations, but that's like a CubeSat unit. And so you can have multiple units. Like you could do 3 and it's like the size of a loaf of bread, or like lunar flashlight is I think 6. And so it's like a cereal box.
Right.
But like the original definition was based on this cubic size.
Got it. And that name, I suppose, has just persisted with time, as they do.
Indeed.
Yeah. Cool. Well, and I think this was very cool, Tara, because you have worked on, a lot of missions, right? You've kind of been involved. Have you ever done anything with CubeSats before?
I just started. So, so I've done... It's totally opposite, because I've done Europa Clipper, which is the giant flagship mission going all the way to Jupiter. But now I'm working on Lunar Flashlight, part of the Artemis program, which is a CubeSat.
Nice.
And so it's going with some other instruments on Artemis 2, I think. And then it'll be deployed, and then it's just going to orbit around on its own and do this. So yeah, I'm learning a lot about CubeSats and instrument design and all sorts of fun stuff like that. So yeah, this was super fun to talk to.
This is really relevant to what you're doing right now. That's pretty neat.
Yeah, it's a nice perspective.
Oh, sorry.
Oh no, go ahead.
I was just going to say, in the interview, we briefly talked about using CubeSats as impactors so that we
Yes.
Are you doing anything with impacting CubeSats or not quite?
Not yet, I'm not. Did you see my face when he said that? I was like,
Scientist Tara has entered the chat.
Impact, you mean I could just throw it at a planet? Yes, totally something I would love to do, is just crash a CubeSat into the moon. I'm sure there's probably rules. I know we did it with a bigger satellite. We smashed things into the moon, and we smashed a lot of things into the moon, not on purpose.
Yeah, there was that whole thing about like life on the moon now, because I think it was a Chinese satellite around the moon crashed and released like some tardigrades or something. Little water bears.
I'm not convinced that tardigrades weren't there to begin with. So, tardigrades are everywhere.
Well said.
I love them.
So
no, what I was thinking is, when he was talking, and I guess you guys will hear this in a minute, talking about how easy it is to launch a CubeSat and how, elementary schools and stuff are doing this work. We need a Fisk CubeSat. We should put a video camera on it and launch it into space for our next full dome film.
I
see John is super excited about this. I bet our production guy Thor would totally be into it. We need to figure out a way to get a Fisk CubeSat into orbit.
So Tara, you talked about the lunar flashlight being a part of Artemis 2, right? Which is an Artemis mission, and if I'm not mistaken, should have people on board. Is that correct, or are we talking about something else?
This is pre-people, so
okay.
We're planning. I think Artemis 3 is the one that's going to have the astronauts on it. And so
Okay.
that's like 2024-ish.
Got it.
2, I think we're still looking at a 2022 launch. So this will be the first one pre-people.
Sure.
Or I guess the last one pre-people.
Right. Yeah, depending on which direction you're thinking in. So when you put a CubeSat or any instrument on a vehicle that is carrying astronauts, is there like just like a payload compartment that has instruments on it or a spacecraft in it? Or how does that work? How do you coordinate humans and also spacecraft?
I'm not 100% sure how all of that works. I would imagine, since I don't know, it probably depends on the launch vehicle too, which, we're still not 100% sure if SLS is going to get off the ground. So it probably depends on the launch vehicle, but I'm thinking like with something like Orion that's going to Mars, they've got all the people are up in the little kind of nose cone part of it in the little capsule, and that leaves you a whole big stage where you could put other stuff, especially if you're just kicking stuff off like as you're leaving the atmosphere. You could do something like that. I would think it would be doable. You probably couldn't take too many because of weight restrictions and things, but I don't see why not. I mean, they're very small.
Little babies.
They're teeny.
When we talk about Artemis 2, just a quick aside, so is it not confirmed that will be SLS?
I don't know enough to say. Let me put it that way.
Okay.
It's a constantly evolving situation, especially since they just did that big test. So it's really hard to say, and I'm not inside enough to know.
Okay. Well, then I guess we'll find out as
So,
time goes on.
yes, stay tuned.
Cool. Well, I suppose we should go ahead and jump into our interview, huh?
Sounds good.
Let's do it.
All right. All right, so today we are talking with Dr. James Mason, who builds and flies small satellites for NASA. His first hands-on experience came as a PhD student in the Aerospace Engineering Sciences Department at CU Boulder. And he continued that after graduating into a postdoc at NASA Goddard Space Flight Center, and is now back at CU's Laboratory for Atmospheric and Space Physics, which you may know of as LASP. He's worked on 17 CubeSats to date, which have observed everything from solar explosions to exoplanet host stars. He's contributed to the engineering, fabrication, communications, operations, science, and outreach in all of these missions, and is now the principal investigator leading a CubeSat called SunCET. So we're super excited to talk with you today, James. Thanks for joining us.
Yeah, I'm excited to be here. Thanks for having me.
Awesome. Well, I figured we'd start with the obvious question. Can you tell some of our listeners what exactly is a CubeSat? This is not something that a lot of people know about.
Yeah. Hopefully that'll change after they hear this podcast. And CubeSats are on the rise, so I imagine a lot more people will know what they are. But the super short answer is they're just small satellites. Most satellites are about the size of like a small car, and these ones are like bread loaf size-ish. The smallest unit, a single unit of a CubeSat, is a 10 by 10 by 10 centimeter square. And a lot of CubeSats are 3U, so they're just 30 centimeters, so like a loaf of bread. And now very popular are 6U. Those are probably the biggest up and coming region right now. And they do all sorts of things, all the same sorts of things that you'll find in a big satellite, you'll find in these little ones too, just like an ostrich and a sparrow are both birds. These are both satellites. So yeah, they do science, they do communications type things, they do a lot of technology demonstration. So yeah, they're really cool and educational as well, because they're smaller. They're also way cheaper. And so there's even been elementary schools that have launched these things into orbit.
That's super cool.
So in addition to them being so cheap, to use and launch, what other advantages, does a small satellite have over the traditional large satellite?
So the biggest advantage, well, there's a lot, but one really important one is that you can fly many of them for the same price that you would have to pay for like a single Hubble, which is like $1 billion or whatever. You could fly hundreds or thousands of these things no one's done that so far, but we can actually do constellations, and there are CubeSat constellations up there now that wouldn't be possible to do if every single spacecraft cost $500 million or whatever. And that allows you to do all kinds of different things. Like if you want to get images of the whole Earth, like every hour, you can do that. There's a company that's their whole thing called Planet. They used to be called Planet Labs, and they have, I think, hundreds of CubeSats up now. They call them doves, and they're imaging the Earth all the time. So basically the end goal is that you'd be able to update Google Maps, like Google Earth, the whole thing, like every day instead of like every 5 years.
And
Wow.
can these very small units, I mean, that seems like, you know, getting full planetary imagery. I don't know, maybe I'm out of touch with how good technology is. That seems like it'd be hard to put such a powerful camera on such a small little unit.
Well, the camera in your phone is like basically what they start with. Actually, that company was founded by engineers at NASA Ames. So I worked at NASA Goddard Space Flight Center, which is just outside DC. NASA Ames is another center in Silicon Valley. And so those engineers worked on, I think it was called PhoneSat, where they literally took an Android phone, stripped away the casing and some of the extra stuff they don't need, and then used that as the main processor unit for the spacecraft and its camera and everything. So they then spun off to create a company based on that, and they called it Planet Labs. And they've basically taken the same mentality. Like usually when you see photos of people working on satellites, they're in these clean rooms and they have full bunny suits on. And but at Planet Labs or Planet, they're much more cavalier with them because they're like phones. So there's enough power there. The miniaturization of technology that's been happening in the commercial world has really enabled the power that you need to run a satellite.
That's crazy cool. So as somebody who works on these missions, 17 missions now with these CubeSats, are there like particular topics or questions or missions that CubeSats are particularly good for?
Yeah. Actually, if you look at the history of what NASA has done with these things, they were a little bit slower to start than, for example, the National Science Foundation was funding these things a little over a decade ago, because they're very education oriented. So they were funding teams, including one here at CU. Our first CubeSat was an NSF CubeSat called CSSWE. And then once they started proving themselves out, NASA was like, okay, it looks like we'll be able to do real science with these things, but there's still some types of things that they're better for until technology continues to improve. So for example, like Earth observing things, or things looking at the magnetosphere around the Earth, or energetic particles in the Van Allen belts and all those sorts of things. Those are pretty easy to do because you don't need really fine pointing usually, and the instruments are already pretty small. So our first CubeSat, CSSWE, was one of those. And also anything looking at the sun is relatively easy to do because the cameras you need are not big. Because the sun is literally the brightest thing in the sky. So usually we're worried about our instruments degrading from the number of photons rather than needing a big aperture and big mirrors and things to collect light. So that lends itself to small platforms like CubeSat. So a lot of the early NASA missions have been Helio. And the first one I worked on in grad school was one of those called Minx. And it was observing the sun in soft X-rays. And now in the last few years, NASA has started to get into astrophysics as well, because the pointing of the spacecraft has gotten good enough that they can actually point and stare at the same spot long enough on these tiny CubeSats to collect light for a long time, even though the platform's pretty small. And planetary too. Really quick,
how do you point a CubeSat? Like what makes the motion happen, and how does that get better with time?
This is actually the same way you do it on big spacecraft, which is just everything's physically smaller. So there's a few different ways to do it. The most common is what are called reaction wheels, which are just gyroscopes. So they're spinning wheels, and in space there's, quote, no gravity. So if you spin a wheel going this way, the thing that's holding onto it will start spinning the other way. So if you put 3 wheels all in different perpendicular to each other, then you can have 3-axis control over the spacecraft that way. But over time, everything in orbit does experience drag still from the Earth's atmosphere. It's very, very tenuous out there, but over time there is drag. And so that eventually, as you're trying to fight that small amount of drag and the small amount of pressure you get from photons from the sun, the wheels will just need to spin faster and faster and faster to keep pointing where you want them to go. So periodically you have to dump all of that angular momentum. So to do that, they have little electromagnets that are, again, 3 rods perpendicular to each other. And they basically turn on to grab the Earth's magnetic field to hold it steady while the wheels can slow down. And then they can let go and the wheels can go again. So that's how most spacecraft point. And if you're in interplanetary space where you don't have a magnetic field, they'll use thrusters to do the grab to hold steady while the wheels slow down.
I imagine that those electromagnets have to be super powerful in order to grab the Earth's magnetic field. Is that true, or is the Earth's magnetic field a lot stronger than I think it is?
It is pretty weak. But I mean, because it's a CubeSat, they can
Right.
only be like tiny little, like
Right.
8 centimeters or long, 8 centimeters long or so. So they're not crazy powerful, but they're not super weak either.
Right. Man, that's pretty cool. So, okay, in addition to, what we just talked about, right? And I guess actually that is easier if you have a smaller box because there's less momentum total, but maybe not because the components are smaller. Anywho, what are the other, I don't want to say disadvantages, but challenges of building such small satellites when in a larger satellite, you have more space for larger components and other such things?
So I'd say the number one is budget, because these things are physically smaller. They're also typically much cheaper, like I said, which is an advantage, because then elementary schools and high schools and undergrads and grad students can actually work on real hardware. Whereas like with James Webb, when you're talking about $10 billion, it's like, no, seasoned, experienced professionals only, please, because mistakes here are extremely costly. But on the flip side of that, the fact that everything has to be kept cheaper means that lifetimes in the spacecraft are shorter. So usually we can't use the standard aerospace things that are radiation hard or radiation tolerant. So once they get on orbit, they won't last as long. They'll eventually die. And then one other thing, just a practical thing, is that because they're so small, it's hard to get your hands inside to like do things. So like everything's just miniaturized. So of course there's like small electronics and things inside big spacecraft as well, but working everything being in such a tight little space can be challenging.
I wonder, it sounds like every talk about using like camera phones and these things, we can't make them radiation safe. It seems like they're almost sort of disposable spacecraft in a way.
Mm-hmm. Yeah, so I would say there's different approaches to it. Some really, like, failure is an extremely unwanted outcome of these things. So they'll put more money in development and testing into making sure it really will succeed. And then on the other end of the scale are people like Planet, who are just like, whatever, we know some of these are going to fail and it's not a big deal because we're replacing them all the time. And it also enables, and one of these other advantages beyond just constellations, with them being so cheap, is you can do things with them that you couldn't do with expensive spacecraft, like intentionally fly them into the surface of the moon or Europa or otherwise, just as impactors. And then you have another instrument, a CubeSat or a bigger spacecraft, that's observing that and can get like spectra as the dust plume flies out. So in that sense, they're very disposable. And the planetary mission I alluded to earlier, NASA has done one of those now as well. Another one of the NASA centers, Jet Propulsion Lab, they flew with the InSight lander that arrived a couple years ago at Mars. They flew 2 CubeSats independently alongside it, so that when it was going down into the atmosphere, they would have a radio relay through the CubeSats. They called them Marco. And yet, to me, that's still like the most, I mean, I've worked on 17 CubeSats. I've been very hands-on with a couple of them. So they're like my baby, but still this Marco pair of CubeSats is my favorite ever, because they're just amazing. And they took their own photos of Mars and everything. They flew on their own. They're like the size of a shoebox, and they flew to Mars. It's crazy.
That's so cool. I'm imagining them like, you know, as getting real like awesome video of things crashing through the atmosphere and just having them, you know, little remote control cameras.
Yeah, exactly.
From a filmmaker standpoint, that's super exciting.
Yeah, extremely. And that's another thing. It's like, I mean, they were disposable. They had their like 20 minutes of purpose when InSight was going down through the atmosphere, and then they flew off past Mars and like never talked to them again. But it's something you couldn't do if you didn't have miniaturized technology with CubeSats.
That is super cool. So these CubeSats, this is a pretty new thing, obviously. I think they've been, the first one that I could find was around like in the late 90s when they started making these tiny, tiny things. Are there any like specific technologies or anything that had to be developed before they could start this extreme miniaturization?
Yeah, so yeah, the first ones were in the late 90s. The official definition for what defines a CubeSat came out in the early 2000s from Stanford and Cal Poly. And Cal Poly still is the maintainer of the general standard of like what dimensions do you have to be considered a CubeSat. And there's some competing ones now as well, but they're pretty well established now. But the main technologies have been driven really by the commercial side, just like our phones have really shrunken. But you know, that was happening in the late 90s, early 2000s. We started getting small processors that could do these sorts of things. And that's mostly what a satellite is some flying electronics and usually a camera or some other sort of sensor. The other big two innovations that have happened in more recent years, like in the last decade, are pointing and radio communications. So the pointing one we talked about before, you have those 3 wheels. So those weren't available in CubeSats until a few years ago. And you sort of had to do it on your own. You could buy the little wheels, but then you had to develop all the algorithms for first knowing where you're pointing, which requires other sensors and things. And then controlling the reaction wheels and the torque rods, they're called, for dumping momentum. So all of that's very complicated and has been drastically reduced in complexity now that you can just buy a commercial off-the-shelf part to do all of that for you. This from another company in Boulder called Blue Canyon Technologies, is like one of the really prominent ones. There's another company called Maryland Aerospace that designs similar systems. So that's been like unlocked all sorts of new possibilities and time too for the CubeSat developers. Now that you don't have to build your own pointing system, you just buy it.
Is that something that you do a lot with CubeSats, is just get this like off the shelf technology? Yeah,
that's been one of the big enabling things too, is the industry has really latched onto these things. It's like there's a real market for these. So more and more you can just buy. I mean, you can literally now just buy a satellite and then fly it if you want. But usually what people do is buy it and then put some stuff in it to make it do something beyond just be a beaconing, blipping satellite. Put a camera or something and some sort of instrument in there. So yeah, you can just like there's one website, one of the very early ones called Pumpkin, that's still around, where you can buy everything to build a CubeSat. There's one in Europe that's unfortunately called ISIS, but they sell like everything that you would want to build a CubeSat. There's vendors like Clyde Space in the UK. Here in Boulder, we have Blue Canyon, which now does more than just a pointing system. You can buy the whole spacecraft and they'll do operations and communications and everything for you as well. So a lot of this stuff has become like you can just go shopping and you can develop stuff. You can develop whichever part you want. For example, to train students how these things are put together, but you don't have to if that's not where you want to put your time and effort.
I guess that's part of what makes it easy for like elementary schools and, you know, classrooms and stuff to be able to do this. They don't have to machine and mill and all of that.
Yeah, exactly. And that was the point of the CubeSat standard in the first place. It was to make it so students could learn and it was more accessible for education, but also so that there'd be a standard, because every NASA satellite, every NOAA satellite, every DoD satellite, every one of them is unique. And so it's like you have to start from scratch every time. Of course, there's commonalities and things, but CubeSats were intended like, no, you're going to be these dimensions. You can have like these protrusions in places, to just standardize things so that vendors and the industry could define like, okay, we'll sell you a board and it'll be compatible because it's going to be this big, it'll only consume this much power, etc.
So we're talking about how almost everything, all the components that you want, you can buy off the shelf now, right? That there are a lot of companies manufacturing, components that you can pick and choose from. I'm imagining that you cannot purchase the means to launch your CubeSat off of the shelf. Is that correct? Or are there ways that you can buy a launch, whether that's a rocket or you can how does that work?
Yeah, so the answer may surprise you. It's mostly yes now, that you can pretty much just buy a launch if you have a lot of money. So the normally costs are like $50 million or more, or a lot more if you're a big mission. But SpaceX now is doing such regular launches that you can get like, I think it's like 150 or 200 kilograms of mass for $1 million. So that launch cost is like way, way, way lower. Still more than like, yeah, I'll just whatever. It's the model rocket price. It's not that low.
So you are still buying space on a rocket that is being professionally flown. You're not just somehow purchasing your own means of launch and doing it in your backyard.
Right. Yes. Yeah. So you still have to go to one of the main vendors, the ones that, everybody's heard of SpaceX. Now Blue Origin is coming online with their own orbital thing. So it's still big companies that are doing these things.
Sure.
The other way to do it is like if you're, you can get it for free if you're some sort of educational institution. So NASA has a program called ELANA, which is the Educational Launch of Nanosatellites. And you just write it's like a 2-page proposal or something like that. And you say we're a university or we're an elementary school or whatever, and we would like to put our thing in orbit, please. And they have a very high acceptance rate. So they'll say, okay, and they'll find you a launch and you don't have to pay for it. And it's a ride share. So it'll be some rocket that's going to be going up anyway. They almost always have the ability to carry more mass into orbit than they have from the main payload who's paying for the launch. So they'll happily sell you some space for $1 million with SpaceX, or through Elana. NASA just takes care of that part for you. So yeah, it's pretty cool that we call them ride shares.
So when there's this extra space that you can sell off to people that want to launch a CubeSat, right? Or if you're NASA, you can give it to someone because they're kind that way. How do things fit together in a rocket like that? Like, I guess I've always imagined, you have like one main payload and everything else is built to support that payload. Is it, more general than that?
So I highly recommend looking up some YouTube videos of this because it's really awesome. One of the other advantages of standardizing CubeSats is the outer dimensions are known, so they can build deployers for them that are also standardized. So they'll have the main payload, which is usually a cylinder or a big cube in the center, and that deploys off. And then they have these usually like big rings of deployers that are just rectangles like Pez dispensers or something. And then they just start shooting out CubeSats that are literally just spring loaded. So there's a big spring in the back. They open the door and then it just pushes them out. They also have these things on the space station, so you can get deployed directly off the space station. And it's the same idea. You're in a big Pez dispenser and the spring door opens, spring pushes you out. And that's where you can get some really awesome videos. When the CubeSat I worked heavily on, Minx was deployed, it was from the space station, and it happened to be at a time when the astronauts were awake. So the British astronaut, Tim Peake, he had his like 4K DSLR looking out the window, and he has pictures of it, like the satellite. I had laser engraved my name and everybody's name, all the students and everybody on the back, and that happened to be the face that was towards him. It was like, oh my God, like I can see my name in space.
And so, it's got to be the best feeling. I love it.
Yeah, it was so cool.
How fast are they launching if you're able to get a picture of the names engraved on the face?
It's usually like a meter per second. So
okay.
It's pretty gradual. They're not super strong springs.
Yeah.
But there's an Indian launcher from Israel, which is the Indian version of NASA. They have a rocket called PSLV, and theirs kicks CubeSats out much faster. And with a lot less control. Those are the videos that are the most fun to watch on YouTube, because they just fire out and it's just like they're tumbling like crazy, and it's a nightmare for the the CubeSat, who then has to dump all of that angular momentum, which can be a challenge, but it's hilarious to watch.
I'll definitely check that out. That's a great thing to know, to go check out after we do this. So returning to your work, it seems to cover pretty much all aspects of CubeSat mission development. How did you end up, so diversified in all of these, different areas of CubeSat industry?
It's kind of one part fortune and one part interest. So I came in with an astronomy degree from undergrad into an aerospace engineering sciences department here at CU as a PhD track student. I took this graduate projects course where we were working on a CubeSat. So I happened to show up, and my research advisor had an idea, like right at the same time, we could make this little tiny instrument and fly it on a CubeSat to look at the sun and get soft X-rays. And through that course, I sort of ended up in a project management position, and then eventually became a systems engineer type. And then I was just on it for like years until my PhD. And so over time, I just sort of evolved between different things. I would see something needed doing, like none of the other students were interested in working on thermal and modeling and analysis and things. So I was like, okay, I'll learn how to do that. I've never done it before, but it's all compute, like just another piece of software called Thermal Desktop. So I just figured out how to use that, looked up guides and things online. And of course, LASP has experts in all of these things. So I could talk to professionals about how to do it. And so it was just like a series of things like that, where it was like, I'm interested in learning how to do that and nobody's doing it, so I'll learn how to do it.
And nowadays, when you start working on a new project, right? Because you said we've 17 missions that you've been on so far. How do you decide what role to take in each of those, or is it handed to you?
Like is it most of them have been handed.
Got it. So they tell you, here's what you're going to do, and then you do that.
Well, usually it's so most of those 17 I've been sort of brought in because I know stuff from my experience with these things. So they say, like, can you help us do this? And I'm like, sure. And then some of them I'm leading, so I get to choose what role I want and which things I want to do. Yeah, so it's been like that, where it's just I have interest in all the CubeSats that are doing all sorts of different things, technology demonstrations and science and all sorts of different regimes. But because I built up this like breadth of experience across almost all the different domains of building a satellite, especially in a CubeSat, it means that I could fill a role that's useful, especially for first-time teams where they don't have any of that experience, or they're working in an environment like a lot of universities. They don't have a LASP that's been flying satellites and rockets for decades. They don't have that experience to draw on. So a lot of the ones I've helped have been like that, like in other countries too, like in Guatemala and in Australia, that are like fledgling programs in the nation for aerospace. So they're really trying to like pioneer through that and looking for people to help them out with how to build these things.
So say one of our listeners, like maybe a student or someone like that, wanted to work on a CubeSat mission. What's something they could do to start getting involved in something like that?
How old are we talking about, some listener?
I'd say it was like a college student, like a student at CU.
Yeah, at CU, then there's plenty of missions going on at CU. So there's, especially in undergrad, we have a space grant, is an organization that spans multiple universities, and CU is one of them, where undergrads build and fly small satellites, not always CubeSats, but usually CubeSats. And so that's not just at CU, that's all over the place. I also do judging for the Colorado State Science Fair and Engineering Fair. And one year I saw this lone high school kid had built his own CubeSat like in his garage. So, I mean, the things are getting to the point where you can really do that on your own if you just spend the time on it. There's lots of resources out there if you just start Googling around like how to build a CubeSat. Like Raspberry Pis is like the first place to start, or Arduinos or similar. Like learning how to program those things, that's the core of any satellite, is the processor and the software that's running on it.
So launch aside, how expensive is a CubeSat to build? Like, could any person that felt like it just build it in their garage?
So the cost scale. So the cheapest ones I've ever seen are, like like $5,000 or $10,000. Of course, the capabilities of those are pretty limited. They're basically just like an Arduino or a Android phone or something, plus a little antenna sticking out, and then inside of an aluminum case. And then at the higher end, there's CubeSats that are like big NASA, quote unquote, big NASA missions, that are like $10 million or so. And the ones I've worked on have generally, the first one I worked on through grad school was a little over $1 million. And it was able to be that quote unquote cheap because we were having so many students involved that were, getting course credit instead of getting salary for it. So that's how the cost could be that low. The missions that like I'm leading now that are being proposed, like here's the full cost to NASA, are usually around $5 million, where you're paying everyone that's working on it. And yeah, maybe you'll have 1 or 2 students, but it's not like an army of students doing all the legwork.
Is that something that NSF still likes to fund? Can you write grants for specific CubeSats and things?
Yeah. Actually, I haven't been looking into that in recent years, but I am sure that if they had stopped funding those, I would have heard about it. The budgets for those are usually around like 900,000 or so. So even less than the one that I worked on, Minx, was by a little bit, and CSSWE was one of those. So they were also an army of like 11 students at a time over 4 years or so working on it. And that's how they could build one that was, capable. I mean, they had many scientific peer-reviewed journal papers that resulted from those measurements they took on orbit for 2.5 years on orbit, when it was, designed and proposed to only last, I think, 3 or 6 months, but it actually flew for like 2.5 years before it died. And they even have a paper that was in Nature, which is like the premier scientific journal. So, I mean, CubeSats can do real science, even on the lower end of the scientifically capable budgets.
So looking forward to the next, 10 or 20 years of CubeSat development and the space industry, who do you see as the most influential or marketable customers? I'm thinking like educational institutions or small businesses or large corporations, governments.
Probably, I would still probably say universities, with a huge caveat that it depends on how NASA and NSF and other agencies decide to fund things. They have usually set amounts of budget that grow a little bit over time. And they can choose to either fund fewer, more expensive CubeSats, or they can choose to fund many smaller CubeSats. And I hope they go with the latter, because there's just so many ideas out there and niches that CubeSats can fill that even big platforms, I mean, they could, but the scientific justification isn't strong enough to justify a $150 million mission. But you can still get like really big bang for your buck, basically, with these CubeSats. We've actually have a paper in preparation that's comparing like how much bang for your buck do you get from big missions versus CubeSats. And if you just take like the number of papers that are published per year or the total number, then like, yeah, the big missions, of course, they produce a lot of scientific studies. But if you divide it by the cost also for the mission, CubeSats actually perform much better. Which isn't to say that we should only be doing CubeSats, not at all. It's just that they actually are worth the money, even when they have tiny budgets, because they fill these small niches in science that are just like the perfect fit for a small budget, small platform mission that couldn't be done in other platforms.
I can see that being super useful too, even for like I'm thinking, I'm on a big flagship mission and this instrument that we have is the size of a CubeSat. It's like a small trash can. And all the time I have to worry about, okay, well now there's this antenna in the way of my detector, or it's facing the wrong way because the spacecraft has to do this and that. If I could just like eject it off into space and let it do its own thing, I wouldn't have to worry about all of this. It's very autonomous, and it seems like it'd be so much easier to collect my data when I didn't have to worry about 17 other instruments.
Yeah, that, and also there's another type of thing that you can gain from that is like long baseline measurements. So for example, there's a proposal we have at LASP led by Phil Chamberlain, who would basically like eject a small spacecraft, usually an orb, but it could be a CubeSat or something, that would basically like go really far away, block out the sun, and then you have your camera way behind. So those are called coronagraphs. Usually you have just a circle and you put it on the front of the camera so it blocks out the sun. But that causes a lot of diffraction, which is basically messes up your image. And so you have to have a really big spacecraft to like deal with all those effects. But if you put your occulter really far away, like what we have with the moon, it eliminates those problems with diffraction. So you can like formation flying is what they call it. So you can do that. And there's actually an ESA mission, the European version of NASA, called Proba 3, which is going to be doing exactly that, which is an in-space formation flying coronagraph, which is not a CubeSat, but it's not a whole lot bigger than a CubeSat either. It's like these smaller things that you have to do if you want to, do the formation flying type things, where the budgets would just be massive if you want to formation fly on normal satellite scales.
There's so much ingenuity going on. I love it. That's super cool.
Yeah.
We also wanted to ask you about one of the projects that you're working on now that you mentioned, SunCET. I just saw a paper that came out. I read through the paper and I could use some explaining on some of that. It was a little much, but could you tell us kind of what SunCET is doing and what kind of things you're hoping to questions you're hoping to answer?
Yeah, sure. So this is the first one where I'm the principal investigator, the PI for it, which means I'm like if it fails, it's my fault person. And it's basically to look at eruptions on the sun. So SunCET stands for the Sun Coronal Ejection Tracker. So periodically, the sun basically kicks out parts of the corona in these things called coronal mass ejections. And sometimes they're Earth directed. And when they reach us after 1 to 4 days or so, they wreak havoc. We call it space weather. Satellites can be damaged. Power lines on the ground can be disrupted and blow out transformers, causing blackouts. RF communications, like for airlines and things, are disrupted. So GPS gets impacted. So there's a lot of practical reasons why we care about space weather. So we want to be able to predict these things. But CMEs, coronal mass ejections, have been observed for a long time with those coronagraphs that I was just talking about. But the problem is they block out the solar disk, and they don't just block out the disk, they block out some region around the disk, because you would have to have incredibly precise pointing, and the diffraction would be really bad if you had a disk that was exactly the size of the sun. So that region where they're blocking out beyond the disk of the sun is actually where CMEs experience their greatest acceleration, but we don't observe it. We have imagers that specifically look at the disk in the extreme ultraviolet, and we have these coronagraphs that look off the disk in usually visible light. And in between, there's a gap. And so SunCET's specifically designed to fill that gap. We can observe the disk and off disk, overlapping both of the existing imagers, the extreme ultraviolet ones and the coronagraphs, without having any gap at all. So we can see a CME start, from its initial stages of acceleration all the way through its full acceleration profile. And given that, we can actually constrain the models that we have. We have lots and lots and lots of theory explaining like how might these things be accelerated, but they disagree with each other. And they can do that because we don't have observations that can say which one's right and which one's not. And the answer is probably all of them are a little bit right, but when and at what altitudes and what conditions cause what type of acceleration mechanism to dominate. So SunCET's really designed to, lay those questions to rest.
That was pretty much the questions we had to ask for you, but we have our what we call Capcom Q&A, where some of our listeners will submit questions to ask our experts, i.e. you. So we actually got a ton of Capcom questions for this episode. So we've got a whole bunch of questions from our listeners that we're going to throw at you.
Okay, that sounds fun.
Cool. So the first one is from Sarah from Fort Worth. She wants to know, how long do CubeSats stay in orbit for, and how many are currently in orbit?
First question first, where I can give a nice definitive answer: less than 25 years. That's a NASA requirement and is an international norm. So they're all required to be less than 25 years, so definitely less than that. And usually on the order of a couple years, though it varies all the way from a few months up to 20 years or so. And as for how many are on orbit, thousands, I would say, almost all of which are planet doves, because they've launched more CubeSats than anyone, literally hundreds of them. And then there's lots of universities and things that have launched these things as well as like Lockheed Martin and companies have launched some too. And NASA is starting to launch them from their own centers, like Marco I talked about, but also NASA Goddard and others have launched some. So I don't know the number off the top of my head, though I would expect it to be thousands.
And regarding the 25-year rule, or whenever your mission ends, how does it end? When your mission's over, do you deorbit, or do you like move outward away from the zone where people want to be orbiting?
Yeah, so I mean, this is not just CubeSats; it's all spacecraft, and usually big spacecraft have propulsion systems. Not always, but usually, so they have the option to move out. Usually CubeSats don't have the space or the risk profile to put a propulsion system on board. So they can't leave orbit, like go out. Instead, they have to go into the atmosphere. And the 25-year rule doesn't really care which direction you go. You just have to be not becoming space junk. And usually the way for probably 99% of all CubeSats, they passively deorbit, which is just over time, that small amount of atmospheric drag that they experience adds up, and their altitude lowers and lowers and lowers, and eventually it becomes like an exponential. And I actually have plots of this for the Minx CubeSat where I animated it, and it's just like it falls off a cliff. Once it gets to like 300 kilometers or so, then there's like days left. So yeah, they fall back into the Earth's atmosphere and they burn up. And there's other requirements there where you have to demonstrate and calculate the probability that any of the spacecraft is going to make it to the ground, because it could fall through somebody's house, and that's not good. And that does happen sometimes with big spacecraft. Almost never like somewhere where people are. It's almost always the ocean. But because CubeSats are so small, I don't think there's been a CubeSat part that's ever returned all the way to the ground. But you have to show the calculations of all the densities of all the parts inside to show that no, nothing should make it to the ground.
Sure. Cool. Okay, good. And so Ray from Austin is asking, are there ever system failures?
Definitely yes. Because the budgets are small, because oftentimes it's inexperienced teams learning how to build a satellite at all. The budgets being small really impacts the time you have to test. So the biggest mantra we have in any sort of aerospace things, it's like testing is prime. Like design and analyze all you want, but really the most important time you spend is once everything's built, putting it in vacuum chambers, putting it on vibration tables, and like trying to get it to break on the ground where you can still fix it and improve it. Because once it's in space, if it breaks, then unless you're Hubble, that's it. You'll never be able to repair it or replace anything. So they do fail more often than anyone wants. I mean, we sort of accept the higher risk in CubeSats as part of the just the cost of doing them, and it hurts when they fail, but yeah, it's just part of the learning experience, I guess.
So Mick from Boulder asked, has 3D printing been a useful technology when fabricating small satellites?
Definitely. We actually, on Minx, the one I spent most of my PhD time working on, we had two things that were 3D printed. Not in plastic, though we did prototype in plastic. But we paid a company in Colorado, I can't remember their name, but 3D printed in metal, laser sintering. And we printed the hinges that the solar panels would, like, they fold out and they point at the sun. So those hinges were 3D printed in stainless steel. And the housing for our secondary instrument, that was like a fine sun sensor to like get really high precision pointing on the sun, pointing knowledge. The housing for that we 3D printed in aluminum. So yeah, it's really useful for prototyping things. It's really useful for making displays that we take to like conferences and things. Like, check out our CubeSat. We've printed it in like partially clear and all these colors, and it looks really cool. For sizing things, for getting how things can fit together. So we have used it for that. I know lots of other universities are doing the same thing. And yeah, for going to space, like you can actually fly 3D printed metal stuff.
Seems useful.
Yeah.
So Clayton from Houston is asking, what's the tiniest body a CubeSat could orbit?
Oh, that's a really good question. Actually, yeah, I think that would be the same for any satellite. As long as you reduce your velocity enough, you can orbit anything you want. Of course, I mean, if your spacecraft is more massive than the body that you're trying to orbit, that doesn't work. The thing will orbit you. But yeah, so like you could send CubeSats out to like the tiny stuff in the asteroid belts, and I'm sure you could set up the orbital trajectories so that you orbit them.
You could have like a 1-unit CubeSat orbiting a 3-unit CubeSat or something like that.
Yeah, right.
Nice. James from Denver has an interesting question. Could tiny satellites like CubeSats be a threat to national security?
Huh. I'm trying to think of ways that they could be.
Can you legally answer that question?
I think so. The only things I could see them being used for as a threat to national security is like, but it would be stupid, is to like use them to attack other satellites. But you don't need a CubeSat to do that. You just need a piece of block aluminum or something. I guess they could also cause RF jamming in orbit, but you can do that from the ground too. So there probably is some ways, but none are coming to mind immediately.
Yeah, the only thing I thought of was maybe like spy camera kind of things. They're really small, so maybe they wouldn't be detected passing over a military institution or something.
Yeah. Actually, there's I think it's to NOAA of all places, the National Oceanic and Atmospheric Administration. If you're in the U.S. and you're going to launch a CubeSat, so we've had to do this a bunch. If you have any kind of camera on board, even a star camera, which is not intended to look at the ground, but you have to get a waiver or sign forms saying that like you're not going to be using this to surveil, because for those reasons.
Does the imagery that is taken from these cameras go through some middleman, like NOAA or someone, before it's published ever? Or if you sign the waiver, is that enough? And then it's like we promise that we won't do this.
Good question. I've only been on ones that have gotten a waiver for it, because in every case I've worked on, they've either been incredibly low resolution things like 3 pixels of the Earth, or star trackers. And in all of those cases, the waivers did not require us to send anything through NOAA beforehand.
Got it.
But
okay.
If you don't get a waiver, then maybe the answer is you do have to get NOAA involved in the pipeline somehow. I don't know.
Yeah, right. Look, here it is. Here's our picture. It's of space, not you. Okay. Yeah. David from Charlotte, North Carolina is asking, is there a satellite air traffic control system? I mean, it's got to be getting crowded up there.
Yes, it's called JSPOC, which I don't remember what that acronym stands for, but I believe it's the Air Force runs it. And basically they have radar on the ground. It's not just spacecraft that can control anything. It's all anything in space orbiting. They're tracking that's above a certain size. So they're tracking all the space junk, and they do that so that they can issue warnings. So like for every one of the missions I'm on, we've registered with them, told them like that piece of space junk is us. And if you detect that there's going to be any collisions occurring, please notify us. So they provide that service as well. And most spacecraft, as I said earlier, have propulsion, so they can actually move to not impact each other. But yeah, so they don't all the way they don't command people to go into different places, so that aspect of like airspace, air traffic control isn't there, but they are like air traffic monitoring and notifying.
Seems useful.
Yeah, very useful. Actually, that's how most CubeSats track themselves at all. So if you don't have GPS on board, that's like downlinked with your data, you don't know where you are, except that there's these radars that are tracking everything. So once you figure out, okay, they say that this is our two-line element, TLE they're called, which gives you all the orbital parameters, to be able to predict where it should be for the next 24 hours or week or whatever. And then when we point our radio antennas at that, we actually communicate with the spacecraft. So, okay, that one must be us. That TLE is valid for us. And then you just periodically download new TLEs from JSPOC. And that's how you keep track of your spacecraft. So most spacecraft have GPS or some other form of doing that, but CubeSats, it's like, this is a free service. Why would I bother?
Save the space, save the weight.
Yeah.
So Mac from Boulder asks, what is the feasibility of interplanetary CubeSats?
100%, because JPL already did it with Marco. Though to my knowledge, those are the only two that have gone so far. But I believe there's plans to do more.
From myself, do you think that will ever, cross into the realm of education, even like pre-college education, interplanetary CubeSats, or will that always be something, or at least for a long time, something that kind of stays with the, wealthier parts of CubeSat deployment?
I would predict the latter, just because anything going interplanetary is necessarily way more expensive, because you need propulsion systems, and then also navigating through interplanetary space is way harder than just knowing where you're pointing in Earth orbit and using those TLEs and things. So it's just the challenge is like order of magnitude or more greater than it is to put something in low Earth orbit or even in geostationary orbit. So it'll probably remain in the realm of like not student led for a long time, but I could imagine with launch costs coming down and especially more missions going to more distant places, like Artemis going with periodic launches from NASA going to the moon. If you can get that far, it's not too much more energy that you need to like get all the way out of Earth orbit and go beyond. And similarly, like with SpaceX planning to go to Mars more often, you could do the same thing, ride-alongs potentially. So that would drive a lot of the costs down.
But unfortunately, you probably can't get JSPOC to auto-monitor your interplanetary CubeSat. You'd have to do that yourself.
Yeah, you'd have to do that yourself.
It's a shame.
I imagine propulsion would be something to consider too, because I've seen like most of the CubeSats that I've seen have solar panels, and that's only good for a certain distance.
Yeah.
I can't imagine them putting plutonium on a CubeSat.
No, there are small thrusters that that are specifically designed for CubeSats, and some of them have already flown. And there's even solar sails that have been tested. There was a Kickstarter that I put like $20 into or whatever from the Planetary Society called LightSail and LightSail 2. It was a 3U CubeSat that deployed this massive solar sail, and it's on orbit right now, taking pictures of Earth and stuff. And so that's another potential method to do relatively cheap but low thrust propulsion through interplanetary space.
Okay, and our final question comes from Samuel in Boston, who asks, it seems that one of the big things that made CubeSats so revolutionary was their miniaturization and standardization that they supplied. Do you, Jason, see CubeSats continuing to update this way, either adapting a new base template like USB connectors did over time, or resizing as technologies and capabilities arise? And if not, will something else replace them?
Yeah, I see the standards continuing to. I mean, they've bifurcated a little bit because each deployer for CubeSats, they'll often like have nuances that are different, slightly longer, or they can have a different kind of protrusion, like a tuna can sticking out the end, or they have a different way of connecting to the rails. So there's like 3 or 4 different kinds of things like that. But for the most part, they've stayed together as a collective of what the definition is. So you can mostly do a design, at least in the early stages of a CubeSat design, that's compatible with all of them. And then in later stages, like make the tweaks once you have a better idea of which one you're gonna actually be flying from. And with companies like really scaling up, like Blue Canyon in particular is like getting massive now. They've got like 400 or 500 employees now, and they just started around the same time I started working on Minx, like about a decade ago. And they were just bought by Raytheon. So now they're like part of a massive company. And so they are driving like a lot of standardization as well, because so many people use their pointing system. And so whatever they decide is like the software interface and the electrical interfaces and things, what most people will end up using just to be compatible with them. And that's true for a lot of the other companies too, like solar panels from Clyde Space and others, where as they become like de facto standards of like these are the solar panels or whatever that you buy, however you interface to those become the typical like non-official standard that most CubeSats will design to.
Cool. Well, I think that just about wraps things up. That's the time that we have. So Dr. James Mason, thank you again so much for joining us. It was a pleasure to speak with you.
Yeah, thank you for having me. This was really fun.
All right, so that was our interview with Dr. James Mason. We want to thank him again for joining us. It was really fun talking to him. Be sure to come back next week, everybody. We have another awesome guest. His name is Chris Scherpenseal. I really hope I pronounced that right. And if I didn't, I'm sorry, Chris. We'll fix it later. But he does astrophotography. So he's the guy that takes all the really cool pictures of the moon and galaxies and stars and all of that fun stuff. So if that's something you're interested in or maybe want to get involved in, this will definitely be a good episode for you to check out. We also want to invite everybody to visit our website, www.colorado.edu/FISC. There you can find a schedule of our upcoming shows, topics, guests. There's also an option for you to submit your questions for our Capcom Q&A segment. You can do that there, or you can send us an email here at fiscpodcast@colorado.edu. Also from our website, you can donate to the podcast and help us keep going for the rest of this spring and hopefully beyond. We would love to have some financial support in that way. Be sure to check us out on YouTube, SoundCloud, Spotify, Apple Podcasts. I think that was it. I don't think I missed one, but go ahead and check those out. Comment, like, subscribe, do whatever you need to do to make sure you don't miss any of our upcoming episodes. Otherwise, thanks again for joining us, and we will see you next week.